Good day, everyone. We are the Group 9 and this is our report presentation. First of all, before we start in our presentation, let me read to all of you our objectives. Determine the condition for interference to occur, emphasizing the properties of a laser as a monochromatic and coherent light source. Relate the geometry of the two-slit experiment setup and properties of light to the properties of diffraction pattern. Relate the geometry of the diffraction experiment setup and properties of light to the properties of diffraction pattern. State the postulate of special relativity and their consequences. Apply the time dilation, length contraction, and relativistic velocity addition to worded problem. Calculate kinetic energy, rest energy, momentum, and speed of object moving with speeds comparable to the speed of light. Explain the photoelectric effect using the idea of light quanta or photons. Explain qualitatively the properties of atomic emission and absorption spectra using the concept of energy levels. Calculating a radioisotope's activity using the concept of half-life. So our first topic is all about Huygens principle. Huygens principle states that every point on a wavefront is a source of wavelets which spread forward at the same speed. Christian Huygens was a Dutch scientist who developed a useful technique for determining how and where waves propagate. In 1678, he proposed that every point that a luminous disturbance touches become itself a source of a spherical wave. The sum of the secondary waves that are a result of disturbance, determine the form of the new wave. Shows secondary waves traveling forward from their point of origin, he was able to come up with an explanation of the linear and spherical wave propagation, and derive the laws of reflection and refraction using this principle. He could not, however, explain what is commonly known as diffraction effects. Diffraction effects are the deviation of rectilinear propagation that occurs when light encounters edges, screens, and apertures. These effects were explained in 1816 by French physicist Augustin Jean Fresnel. Straight wavefront. Each point on the wavefront emits a wave at speed v. The emitted waves are semicircular and occur at t time later. The new wavefront is tangent to the wavelets. This principle works for all wave types, not just light waves. The principle is helpful in describing reflection, refraction, and interference, shows visually how Huygens' principle can be used to explain reflection, and show how it can be applied to refraction. Huygens' refraction. Huygens' principle applied to a straight wavefront traveling from one medium to another where its speed is less. The ray bends toward the perpendicular since the wavelets have a lower speed in the second medium. Reflection. Huygens' principle applied to a straight wavefront striking a mirror. The wavelets shown were emitted as each point in the wavefront struck the mirror. The tangent to these wavelets shows that the new wavefront has been reflected to an angle equal to incident angle. The direction of propagation is perpendicular to the wavefront, as shown by the downward pointing arrows. Examples. This principle is actually something you have seen or experienced often but just don't realize. Although this principle applies to all types of wave, it is easier to explain using sound waves, since sound waves have longer wavelengths. If someone is playing music in their room with the door closed, you might not be able to hear it while walking past the room. However, if that person were to open their door while playing music, you could hear it not only when directly in front of the door opening, but also on a considerable distance down the hall to either side. It's a direct effect of diffraction. When light passes through much smaller openings called slits, Huygens' principle shows that light bends similar to the way sound does, just on a much smaller scale.
Good day everyone, I'm Jasmine Corios, so let's proceed to two-source interference of light. Interference of light. When two light waves from different coherent sources meet together, then the distribution of energy due to one wave is disturbed by the other. This modification superposition of two light waves is called interference of light. And there pass separate theories of either wave or particle nature. And one of that is corpuscular theory of Newton in the year of 1670, and light corpuscles have mass and travel at extremely high speeds in straight lines. And also Huygens in the year of 1680, and wavelengths, each point on a wavefront acts as a source for the next wavefront. In the study of Thomas Young's double-slit interference experiment, it showed an interference pattern, and it also measured the wavelength of the light. Here is the example picture of two waves interfering. Interference of waves from two sources. The interference of waves causes the medium to take on a shape that results from the net effect of the two individual waves upon the particles of the medium. Wave interference can be constructive or destructive in nature. For constructive interference, the waves must arrive to the point of study in phase, so their path difference must be integral multiples of the wavelength. N equals 0, 1, 2, 3, and so on. As we can see on constructive interference, the waves must arrive to the point of study in out of phase. But for the destructive interference, the waves must arrive to the point of study out of phase. So that the path difference must be an odd multiple of number. So m equals 1/2, 3/2, and 5/2. Double slit interference. For constructive, the bright lights, n equals 0, 1, 2, 3, and so on. And for destructive, the dark light, n equals 1/2, 3/2, and 5/2, and so on. Take note, to find maximum number of fringes, set theta to 90 degrees for n. The light waves emanating from each slit are superposed on the screen. If the waves are out of the phase, then destructive interference occurs, resulting in a dark patch on the screen. On the other hand, if the waves are completely in phase, then constructive interference occurs, resulting in a light patch on the screen. If light is a particle, we set up our screen and shine off a branch of monochromatic light onto it. If light is a particle, then only the couple of rays of light that hit exactly where the slits are will be able to pass through. Imagine it as being almost as true. We are spraying a paint from a spray can through the openings. Since they are little particles, they will make a pattern of two exact lines on the viewing screen. So let's take a look at the second picture. If light is a wave, everything starts the same way, but results we get are very different. And there are still only two light rays that actually go through the slits, as we can see here, but as soon as they pass through, they start to diffract. Remember, diffraction is when light passes through a small opening and starts to spread out. This will happen from both openings. See the picture. So we notice that at some points, the two sets of waves will meet crease to crease. At other spots, crease meets through. Where crease meets crease, there will be constructive interference and the waves will make it to the viewing screen as a bright spot. Where crease meets through, there will be destructive interference that cancel each other out. A black spot will appear on the screen. When this experiment is performed, we'll actually see this as shown as the picture. So we must conclude that light is made up of waves since particles cannot diffract.
Intensity in interference pattern, diffraction and polarization. Diffraction can be described only with the wave model for light. A diffraction patterns occur when the light from an aperture is allowed to fall on a screen. The features of this diffraction can be investigated. Under certain conditions, transverse waves with electric field vectors in all directions can be polarized in various ways. Only certain directions of the electric field vectors are present in the polarized wave. Diffraction. Light of wavelength comparable to or larger than the width of a slit spreads out in all forward direction upon passing through the slit. This phenomena is called diffraction. This indicates that light spreads beyond the narrow path defined by the slit into regions that would be in a shadow if light traveled in straight lines. Diffraction pattern. A single slit placed between a distant light source and a screen produces a diffraction pattern. It will have a broad, intense central band, called the central maximum. The central band will be flanked by a series of narrower, less intense secondary bands. It is called side maxima or secondary maxima. The central band will also be flanked by a series of dark bands called minima. Diffraction pattern, single slit. The diffraction patterns consist of the central maxima and a series of secondary maxima and minima. The pattern is similar to interference pattern. Single slit diffraction. The finite width of slits is the basis for understanding Fraunhofer diffraction. According to Huygens' principle, each portion of the slit acts as a source of light waves. Therefore, light from one portion of the slit can interfere with light from another portion. The resultant light intensity on a viewing screen depends on the direction theta. The diffraction pattern is actually an interference pattern. So the different sources of light are different portions of the single slit. Single slit diffraction intensity. The general features of the intensity distribution are shown. A broad central bright fringe is flanked by a much weaker bright fringes alternating with dark fringes. Each bright fringe peak lies approximately halfway between the dark fringes. The central bright maximum is twice as wide as secondary maxima. There is no central dark fringe. Corresponds to m is 0 in the equation.
Light with a wavelength of 570 nanometers shines on a single slit that is 7.5 meters away from the screen. The width of the central maximum is 3.2 centimeters. How wide is the slit? So first, we have our picture. The single slit, the screen, and the L, which is the distance between the slit and the screen, and the D. Let's say this is the central maximum. And our goal is to calculate D. Now we have the width of the central maximum, which is 3.2 centimeter. So if we draw a triangle, this is y1, L, and theta 1. So the width of the central maximum is twice the value of y1. This is y1. Therefore, y1 is equals to 1.6 centimeters, L is 7.5 meters, and lambda, which is 570 nanometers. We don't know the angle and the D. So let's have this equation. Y is equals to L tan theta 1. So y1 is 1.6 centimeters, which is 0.016 meters. L is 7.5 meters. So 0.016 divided by 7.5, that's equal to 0.002133. So the angle is going to equal arctangent 0.002133. So the angle small is 0.122 meters. Now we can calculate the D. D sine theta is equals to m times lambda. So this is gonna be the sine of 0.122. And m is 1. because we're dealing with the central maximum only. 1 times the lambda, which is 570 times 10 raised to negative 9. So D is 2.68 times 10 raised to negative 4 meters, or in millimeters, 0.268. So let's see if we can get the same answer using other formula since theta is very small. So the formula is ym times d equals L times m times lambda. L is equals to 7.5 and we're finding the d. M is equals to 1. Lambda is equals to 570 nanometers. And since y1 is the half of the central maximum, y1 is equals to 1.6 centimeters. Ym is 0.016 times d equals L, which is 7.5. M is 1 times the lambda, 570 times 10 raised to negative 9. This is equals to 4.275 times 10 raised to negative 6. Divide both sides by 0.016. So D, or the width of the slit, is 2.67 times 10 raised to negative 4 meters, or in millimeters, 0.267. So we almost get the same answer, but the first equation is probably exact, because this is based on saying that sine theta is approximately theta, and also tangent theta is approximately theta, which is basically true if theta is very small.
Intensity in interference pattern. Consider two interfering waves with phase different by phase angle theta. So that is a formula. By superposition, we find the resultant wave by simply adding those formula. We use a phasor diagram to show the vector addition using the law of cosines, but the 1 plus cosine is equals to cosine squared, or the theta over 2. So the result of this are the e2p, which e2p equals to 4e squared cos squared close and open theta over 2. So the intensity is related to the square of electric field through the pointing vector, and that is the formula of it. And the maximum intensity is the 1 equals to 1 sub 0 cosine squared close and open theta over 2. And in terms of the maximum, 1 sub 0 is equals to 2 e sub 0 ce squared. Intensity in interference patterns. What is the phase difference theta at various angles theta from the slits? Think about the path difference r sub 2 minus r sub 1. Whenever this path difference increases by a wavelength, the phase difference increases by 2 pi. Thus, theta over 2 pi is equal to r sub 2 minus r sub 1 over. But the path difference for a slit separation d is just this formula. Finally, then the intensity pattern, since that's the intensity pattern of the interference pattern. So intensity of two slit diffraction patterns. When more than one slit is present, consideration must be made of the diffraction patterns due to individual slits, the interference due to the wave incoming from different slits. The single slit diffraction pattern will act as an envelope for a two slit interference pattern. Interference from two slits are projection of two slit difference onto a screen. A linear dimension of the separation of fringes obviously depends on the angle and the distance from the screen. Here, r is the distance to screen, d is separation of slits, and m is the order of the fringe. Intensity of two slit diffraction patterns. Graph a pattern. The broken blue line is the diffraction pattern. The brown curve shows the cosine squared term. This term by itself would result in peaks with all the same heights. The uneven heights result from the diffraction term. Square brackets in the equation. Polarization of light waves. The direction of polarization of each individual wave is defined to be the direction in which the electric field is vibrating. In this example, the direction of polarization is along the y-axis. All individual electromagnetic waves traveling in the x direction have an electric field vector parallel to yz plane. This vector could be in any possible angle with respect to the y-axis.
Interference in thin films. Interference. It is an interaction of two or more waves at a point in a medium such that the disturbance in the resulting wave is the vector sum of the disturbances in the interfering waves. It is the phenomenon in which two or more waves superpose each other to form a resultant wave of greater or lower amplitude. Interference. It is the interaction of waves that are coherent with each other, either because they come from the same source or because they have the same or nearly the same frequency. Crest of one wave plus crest of another wave at the same point is equal to constructive interference. Resultant wave is a crest whose amplitude is a vector sum of the original wave's amplitudes. Two interfering troughs behave similarly. Crest of a wave plus trough of another wave is equals to destructive interference. If amplitudes of original waves are the same, zero displacement of particles results before and during interference. Thin films. It is a layer of material with thickness in the subnanometer to micron range. It is light striking surface is either transmitted or reflected at the upper surface. Transmitted light may also be transmitted or reflected at bottom surface. Studies of these waves reveal information about the surface, including the thickness of the film or the effective refractive index of the film medium. Thin film interference. The interference of waves reflected from the top surface with whose reflected from the bottom surface. Thin films, such as soap bubbles, show colorful patterns because of interference between light waves. The thickness of the film has to be comparable to the wavelength of light for a nice colored pattern to be obtained. For constructive interference, the two waves must be shifted by an integer multiple of wavelengths relative to one another. And this is the illustration. Thin film of air trapped between two pieces of glass. Monochromatic light incident almost normally on film. Light is reflected from the two interfaces. The eye focuses these two parallel light beams at one spot on the retina. Additional phase difference. A 180-degree phase change in reflection from interface between air and glass. This is equivalent to an additional path difference of lambda over 2. Destructive interference if path difference is equal to odd number of 1/2 wavelength. Constructive interference if path difference is equal to even number of 1/2 wavelengths.
Postulate of special relativity. 1. Principle of relativity. All the laws in physics are the same in all inertial reference frame. 2. The speed of light in a vacuum is the same, 3.0 times 10 raised to 8 meter per second in all inertial reference frame, regardless of the motion of the observer or source. Consequences of special relativity. There is no such thing as absolute length or absolute time in relativity. A time interval or length measurement depend on the reference frame in which it is made. Consider the following thought experiment devised by Einstein. A train box is moving with constant velocity when two lightning bolts strike the end of the train box, leaving marks on the boxcar and ground. Two observers are located midway between the ends of train box, one at O and another fixed on the ground at O. A. Relative to observer at O, the two light signals reach him at the same time, since the light signal traveled at the same speed over equal distances. He concludes that the two events at A and B occurred simultaneous. B. Relative to observer at O, the light signal reached him at different time. Since he is at the midpoint, he observes that the light signals must take the same time to reach him because both light signals travel at the same speed over equal distances. Since the light signals do not reach him at the same time, he concludes that they were not simultaneous. In general, two events that are simultaneous in one inertial reference frame are not simultaneous in a second inertial RF moving at constant velocity relative to the first.
So let's proceed to relativity of times and lengths. The theory of special relativity. Special relativity was developed by Albert Einstein in the year of 1905, and it forms part of the basis of modern physics. After finishing his work in special relativity, Einstein spent a decade wondering what would happen if one introduced acceleration. This formed the basis of his general relativity, published in the year of 1915. The theory of special relativity explains how space and time are linked for objects that are moving at a consistent speed in a straight line. One of its most famous aspects concerns objects moving at the speed of light. Time dilation. In the theory of special relativity, the slowing down of a clock is determined by an observer who is in relative motion with respect to that clock. In special relativity, an observer in inertial motion has a well-defined means of determining which events occur simultaneously with a given event. It turns out that as an object moves with a relativistic speed, a strange thing seems to happen to its time as observed by us. A stationary observer in an inertial reference frame, what we see happens that the clock in motion slows down according to our clock. Therefore, we read two different times, and we come up to the question, which time is correct? Well, they both are because time is not absolute but is relative. It depends on the reference frame. Let's look at the example. There is a set of twins, one an astronaut, the other works for mission control of NASA. The astronaut lives on a deep space, trip traveling at 95% the speed of light. Upon returning, the astronaut's clock has measured 10 years, so the astronaut has aged 10 years. However, when the astronaut reunites with his Earth-bound twin, the astronaut sees that the twin has aged 32 years. This is explained due to the fact that the astronaut's twin is traveling at relativistic speeds and therefore his clock is slowed down. Let's see how we can calculate the time difference. The equation for calculating time dilation is as follows. Now, let's have a closer look at the equation and determine just what impact the speed of the object has on time dilation. We can see that as the velocity is small compared to the speed of light, the quantity B2 and C2 approaches 0 and the equation simplifies to t. So, at relatively slow speeds, our everyday speeds, time dilation is not a factor and Newton's laws are still applicable. Now let's look at the high speeds, close to the speed of light. From the equation that as velocity increases, the quantity of B2 and C2 approaches 1 but will never quite reach it, causing the quantity to become smaller and smaller. Therefore, causing the time measured by the greater observer, TO become greater, thus making our time appear slower. I know it's so confusing, but here is the graph for better understanding. As we can see in the graph, time dilation starts TO show up between 0.4c and 0.5c. Also notice that the closer one gets to the speed of light, the greater impact speed has on time dilation. Notice how steep the curve gets towards the end. The twin paradox. Time dilation, the basis for the so-called twin paradox. The twin paradox asks why a twin traveling at a relativistic speed away and then back towards the Earth ages less than the Earth-bound twin. The premise to the paradox is faulty because the traveling twin is accelerating, and special relativity does not apply to accelerating frames of reference. So now let's proceed to length contraction. One of the peculiar aspects of Einstein's theory of special relativity is that the length of objects moving at a relativistic speeds undergoes a contraction along the dimension of motion. An observer at rest relative to the moving object would observe the moving object to be shorter in length. Length contraction is the shortening of the measured length of an object moving relative to the observer's frame. Here is the formula of length contraction. If we measure the length of anything moving relative to our frame, we find its L length to be smaller than the proper length that would be measured if the object were stationary. So here's the example of calculating length contraction. The distance between stars contracts when you travel at high velocity. Suppose an astronaut such as the twin discussed in time dilation earlier travels so fast. So number 1, she travels from the Earth to the nearest star system, Alpha Centauri, 4,300 light years away as measured by an Earth-bound observer. How far apart are the Earth and Alpha Centauri as measured by the astronaut? So here's the solution of the problem. First, note that a light year, Ly, is a convenient unit of a distance on an astronomical scale. It is the distance light travels in a year. And note that the 4,300 Ly distance between the Alpha Centauri and the Earth is the proper distance, LO, because it is measured by an Earth-bound observer to whom both stars are stationary. To the astronaut, the Earth and the Alpha Centauri are moving by at the same velocity, and so the distance between them is the contracted length.
Classical velocity addition. For simplicity, we restrict our consideration of velocity addition to one-dimensional motion. Classically, velocities add like regular numbers in one-dimensional motion. Next is the relativistic velocity addition. This is the second postulate of relativity, or verified by extensive experimental observation, says that classical velocity addition does not apply to light. Imagine a car traveling at night along a straight road. As it's seen in the picture, if classical velocity addition applied to light, then the light from the car's headlights would approach the observer on the sidewalk at a speed u is equal to v plus c. But we know that light will move away from the car at speed c relative to the driver of the car, and light will move towards the observer on the sidewalk at speed c too. According to experiment and the second postulate of relativity, light from the car's headlights move away from the car at speed c and towards the observer on the sidewalk at speed c. Classical velocity addition is not valid. Either light is an exemption, or the classical velocity addition formally only works at low velocities. The latter is the case. The correct formula for one-dimensional relativistic velocity addition is u is equal to v plus u over 1 plus vu over c squared, where v is the relative velocity between two observers, u is the velocity of an object relative to one observer, and the u prime is the velocity. For ease of visualization, we often choose to measure u in our reference frame, while someone moving at v relative to us measures u prime. Note that the term is vu prime over c squared because very small at low velocities, and u is equal to v plus u prime over 1 plus vu prime over c2. Gives a result very close to classical velocity addition. As before, we see the classically velocity addition in an excellent approximation to the correct relativistic formula for small velocities.
Relativistic dynamics. We are familiar with the idea that physical law must be valid in all inertial reference frames. This is called the principle of relativity. Mathematically, this is guaranteed in different ways for different types of equations. A law written in terms of relativistic scalars. Scalar is equal to scalar. Satisfy this condition, since scalars are the same in all reference frames. If the law is written in terms of four vectors, then we have a covariant relationship, which means that the left and right sides vary in the same way with changes of coordinate system. This also satisfies the principle of relativity. An example of the first is the definition of mass m in terms of the energy momentum 4 vector. Both sides of this equation are scalars. The mass m by definition and the dot product of the 4 momentum with itself via the properties of the dot product. The relationship between the wave 4 vector of a matter wave and the 4 momentum is an example of the second type. The components in different reference frames are different, but the components on the two sides change in similar ways since both sides of the equation are 4 vectors. The relativistic form of Newton's second law is... This is correct, but it is not expressed in covariant form because it is a relationship between space vectors only, and the dt is the time-like component of a displacement 4 vector and not a scalar. This makes the conventional definition of force highly inconvenient in the relativistic context. If the object in question is moving at speed v such that this formula, then we can rectify the second problem by eliminating the increment in time dt in favor of the increment in proper time dt along the trajectory of the object. These formulas so that Newton's second law becomes this formula, where m is equals to F is called the Minkowski force. Notice that the Minkowski force and dt differ respectively from the ordinary force F and the ordinary time increment dt when the object is moving at relativistic speeds. This completes the first step in making Newton's second law covariant. The second step is inferring the time-like component of this equation. This is fairly obvious as p is the space-like component of the 4 momentum vector, the time-like component of which is the energy E, where mt is the time-like component of the Minkowski force. The above equation indicates that mt is just the proper time rate of change of energy, or something like the power. The complete covariant form of Newton's second law is thus: given some force F, it is clear how to compute the space-like part of the Minkowski force. Just set m is equals to F. However, equation is not a particularly convenient way to compute the time-like part. An easier way comes from dotting equation with a 4 momentum, where we have used the fact that the length squared of p is minus the mass m squared. Since the mass of the object is constant scalar, it doesn't change with the time resulting in. In words, mt is just times the power or work done per unit time by the force F on the object. If the position of an object is x, then the velocity is. This expression suffers the same problems as the traditional form of Newton's second law, and we solve these problems in the same way. Eliminating dt in favor of dt, we get this formula. When u is equals to v is the space-like component of the 4 velocity, the time-like component is just these formulas. Where the space-time position vector is x, as usual, note that u is truly a 4 vector as its length is scalar. It is also easy to show that the 4 velocity is related to the 4 momentum by the 4 acceleration is a 4 vector defined as follows. We know that it is a 4 vector because the right side of the equation defining it is also a 4 vector. The 4 acceleration is normal to the 4 velocity. The Minkowski form of Newton's second law can be written in this formula. In the rest frame, it may be shown that the 4 acceleration of some moving object is where v and a is equals to dv over dt are the actual velocity and acceleration of the object in the rest frame. The form the 4 acceleration depends very strongly as to whether the acceleration is parallel or normal to the pre-existing velocity. If the acceleration is parallel to the velocity, this reduces to, for an acceleration normal to the velocity, we have this formula. An inertially co-moving reference frame relative to a moving and possibly accelerating object is a frame moving at the velocity of the object at a specified instant in time, but not accelerating. In an inertially co-moving frame, the for velocity of the object is 0 and the for acceleration is this formula, where a0 is the ordinary acceleration of the object in this frame. Note that a0 is distinct from the above acceleration, a in the rest frame. However, the Lorentz transformation can be used to rewrite the components of a in the rest frame.
The Doppler effect. The Doppler effect is the shift in frequency and wavelength of waves that results from a moving source and or moving observer relative to the wave medium. Consider a point source of traveling waves at some frequency. A source moving towards an observer with velocity. The observer sees wave fronts that are squeezed in the direction of v, but the wave velocity remains unchanged. This is the formula. And another formula, a source moving away from an observer. This is the illustration of Doppler effect. This is another illustration of Doppler effect. An observer moving towards a source with velocity. Here an observer will see the same wavelength but with a higher wave velocity. This is the formula. This is the formula of an observer moving away from a source. In the case of light waves, classical, moving source, this is the first formula. Classical, moving observer, this is the another formula. Makes sense. The frequency is higher if observer and source approach each other and lower if they are receding. But this is a classical calculation. There is an asymmetry between moving source and moving observer. This is the formula of moving source, and this is the formula of moving observer. The relativistic Doppler effect calculation differs from the classical one because of time dilation. Consider a source of frequency f fixed in S. In S, with the source in S moving towards the observer in S, the wavelength in S is, and this is the formula. Now, this is the formula. Still in S, we find the relativistic Doppler effect for the source approaching. The formula. For the source receding, we have, for completeness, consider the source of frequency be fixed in S. In S, if the observer sees the source approaching, we would find this formula. In summary, for source and or observing approaching, the formula. For source and or observing receding, the another formula. In special relativity, the two situations give the same result. There is also a transverse Doppler effect that does not occur classically. This is the first diagram. The second diagram, the third, the fourth one, the fifth diagram, the sixth, the seventh diagram, and the last one.
Photoelectric effect. The photoelectric effect was first documented in 1887 by German physicist Heinrich Hertz and is therefore sometimes referred to as the Hertz effect. While working with a spark gap transmitter, a primitive radio broadcasting device, Hertz discovered that upon absorption of certain frequency of light, substances would give off a visible spark. In 1899, this spark was identified as light-excited electrons called photoelectrons, leaving the metal surface by Thomson. Based on the picture below, the photoelectric effect involves irradiating a metal surface with photons of sufficiently high energy to cause the electrons to be ejected from metal. Photoelectric effect using the idea of light, quanta, and photons. The photoelectric effect is the process in which electromagnetic radiation ejects electrons from a material. Einstein proposed photons to be quanta and electromagnetic radiation having energy E is equals to hv is the frequency of the radiation. All electromagnetic radiation is composed of photons. As Einstein explained, all characteristics of the photoelectric effect are due to the interaction of individual photons with individual electrons. The maximum kinetic energy of ejected electrons is given by maximum kinetic energy is equals to hv minus phi, where hv is the photon energy and phi is the work function or binding energy of the electron to the particular material.
Let's now proceed to atomic spectra. The spectrum of the electromagnetic radiation emitted or absorbed by an electron during transitions between different energy levels with an atom. When an electron gets excited from one energy level to another, it either emits or absorbs light of a specific wavelength. The collection of all these specific wavelengths of the atom is in a given set of conditions like pressure, temperature, etc. is the atomic spectra of atoms. And there are three types of atomic spectra, and they are emission spectra, absorption spectra, and continuous spectra. First is emission spectra. Electric discharge in a gas at low pressure. The gas emits characteristic light and a series of discrete bright lines. This series of lines is called an emission spectrum. Second is absorption spectra. An absorption spectrum is obtained by passing a continuous radiation spectrum through a vapor of the element being analyzed. The absorption spectrum, a series of dark lines superimposed on the otherwise continuous spectrum. Note that the dark lines of the absorption spectrum coincide with the bright lines of the emission spectrum. And lastly, continuous spectra. In a solid or a high-pressure gas like a star or gas giant, the atoms are closely packed. This creates a nearly infinite number of possible electron jumps of deeper amount of energy, such as objects like stars, planets, etc. Emit a continuous spectrum. Intensity of specific wavelengths may vary, but there are no gaps. Absorption and emission spectra. The continuous spectrum emitted by the sun passes through the cooler gases of the sun's photo and the chromospheres. The various absorption and emission lines can be used to identify elements in the solar atmospheres and can also lead to the discovery of helium. Some people ask, how do atoms gain energy in the first place? One way is to pass an electric current through an enclosed sample of a gas at low pressure, since the electron energy levels are unique for each element. Every gas discharge tube will glow with a distinctive color depending on the identity of the gas. Let's see figure 2 below. So as we can see in the picture, gas discharge tubes are enclosed. Glass tubes filled with a gas at low pressure through which an electric current is passed. Electrons in the gas atoms first become excited and then fall back to lower energy levels, emitting light of a distinctive color in the process. It's shown that our gas discharge tubes of helium, neon, argon, krypton, and xenon. Neon signs are a familiar example of gas discharge tubes. However, only signs that glow with the red-orange color seen in the figure are actually filled with neon. Signs of other colors contain different gases or mixture of gases. Scientists studied the distinctive pink color of the gas discharge created by hydrogen gas. When a narrow beam of this light was viewed through a prism, the light was separated into 4 lines of very specific wavelengths and frequencies, since frequency and wavelength are inversely related. An atomic emission spectrum is the pattern of lines formed when light passes through a prism to separate it into different frequencies of light it contains. The figure 3 below shows the atomic emission spectrum of hydrogen. As we can see in the picture, when light from a hydrogen gas discharge tube is passed through a prism, the light is split into 4 visible lines. Each of these spectral lines corresponds to a different electron transitions from a higher energy state to a lower energy state. Every element has a unique atomic emission spectrum, as shown by the examples of helium, He, and iron Fe in the figure T.
Radioactive decay. Radioactivity, which is the spontaneous decomposition of a nucleus forming a different nucleus and producing one or more additional particles. Nuclear equation shows the radioactive decomposition of an element. The numbers beside of those letters are their elements. Nuclear forces. Strong nuclear force holds neutrons and protons together to form a nucleus or counters electromagnetic repulsion. Weak nuclear force operates within individual nucleons and give rise to some kinds of radioactivity. Radioactive decay has its types, which is the alpha particle production. The alpha particle is the helium nucleus. The examples of this are on the PowerPoint. Net effect is loss of 4 in mass number and loss of 2 in atomic number. So as you can see on the first examples, there are 228 and 88 Ra, and 2 He is 42 and the Rn is 286. And as you can see on the below, some are added and some are subtract. Radioactive decay, also a beta particle production. Beta particle is an electron. So these are the examples. Net effect is to change a neutron to proton. So the example from the above is the neutron. So when you convert it, it must be a proton. So gamma ray release. Gamma ray is a high energy proton. Examples of this are net effect is no change in mass number or atomic number. Next is positron production. Positron is a particle with same mass as an electron but with a positive charge. So this is the example. Net effect is to change a proton to a neutron. Next is electron capture. Inner orbital electron is captured. New nucleus formed. Neutrino and gamma ray produced. Net effect is to change a proton to a neutron. So as you can see on the graph, this is the black squares indicate stable nuclei. Decay occurs to move isotopes towards the backline. And lastly is the decay series. So this is the graph which is indicate the decay series from the U to Pb. Each nucleate in series except Pb is radioactive, and the successive transformations shown by the arrow continue until Pb is finally formed.